we're not really doing interviews. This is more of an education. So I'm going to teach you guys all the things that you need to know to succeed at these interviews. And these were the topics that came out as the most interesting to everybody, which was, I guess, makes sense. So it was generally just basic structures, basic algorithms, and then advanced structures and advanced algorithms, plus metastrats. So things not on this list that I don't intend to cover today. Time complexity was not voted for, so we're not doing time complexity today. What else? How to talk to recruiters, not covered, won't be going through that. I forget what else wasn't there, but this is what was there. Let's get started. Basic structures, arrays. This may seem overly simple, but everything that we are about to go through is a necessary kind of foundation for all of the things that we're going to build up to as we go later. So the basic idea here, will words show up? Right. So the thing about arrays, and I'm going to mix between typing and images and everything here. So the basic idea is when you talk about data structures, a lot of people, like the first thing that they'll say is, I don't know what a data structure is. So even before we talk about arrays, I'm just going to say, what is a data structure, right? And let's just even have like that most basic conversation. And I'm just going to list anything that's technically a data structure, right? A variable is technically a data structure. It holds data. An array is a data structure. A dictionary is a data structure. So arrays, those count. Lists, those count. Dictionaries, those count, right? Graphs, trees, literally anything else that you could think of. Stacks, yeah, there you go, stacks and queues. Oh my god, I literally totally forgot about stacks and queues. Yeah, right? So all of these are data structures, and like it sounds complicated, right? But at the end of the day, like even a variable is a data structure. And the basic idea is like, and this is very simple, anything that holds data in any sort of form is a data structure, right? It sounds super stupid, it sounds super obvious, but keep that at the back of your mind. So the reason for different kinds of data structures are different kinds of priorities, right? So like, what different priorities can you have, right? Sometimes the priority is speed, right? So I care about how fast I can get the answer to a certain question. Can I answer a question, right? And those questions can be anything, right? Those questions can be as simple as like, right, how big is this? Or, you know, is this item in the structure, right? And depending on how you lay out the data, depending on how you move all of these things, the answers to these questions change. And so the key understanding of why all of these structures exist is to simultaneously represent data differently and give ourselves ability on different priority. Sometimes the priority isn't speed. Sometimes it's just size. How little space can we use to store this, right? That's where you get shit like representing entire like names as singular bits, right? And all that kind of complicated stuff. We won't go through that today because that can be tough. And yes, totally. A dictionary is, in some languages, what is called a hash map in others. So understanding in the back end, like these are the two things to keep in mind, right? The two kind of core sentences are a data structure is anything that holds a data structure is any structure that holds data. That's the first definition. And the second definition, the second thing that we need to understand is different structures exist to optimize different things. That's it. That is the absolute core of the things that we need to understand coming into this, right? All right. So this is our background, right? This all seems obvious. This all doesn't seem like it needs to be said, but I promise you, I will continue referencing these things as we move along. So going back to our list, let's start just talking about arrays, right? And I promise you, if this seems boring early, it will ramp up. Now, arrays are pretty straightforward, right? At the end of the day, an array is just a list of a bunch of numbers in whatever manner you might put it. There's not really much structure, right? Each element, right? So let's kind of give this a definition, right? So each element, right, which means each thing in the array is a single data point, let's say, right? It's just let's just pretend that they're all integers, right? They're all just a single piece of data. Yeah.
You can store like a list or array can store like nested list, right?
Yes, there's a lot of things that you can do with arrays in all kinds of languages. So really, you could just say any element is, in most languages, an object. And let's just, for the sake of this, focus on arrays that are always the same type, right? So, yes. So let's just, for this argument, let's say same data type, right? Because we're going to understand how arrays really work internally very quickly, right? So the size of an array is predetermined. Right? So this means when you make an array, you know how big it's going to be. Or the moment you instantiate it, it has a defined size. Arrays cannot change size. If an array is changing size, that is not an array, that is a list. And we'll get to that later. Some places, some languages will call them an array list, whatever that might be, but at the end of the day, a core array is a predetermined, fixed size. Ah, dang. Move it over a little. There we go. So, that means that it cannot change the size, right? Now, the important part of this is let's talk about what this looks like literally in memory. What does an array literally look like, right? In very literal terms, here's a giant brick of memory, right? Here's address. Ugh. Oh, let me pull out the text. Here's OX00 or whatever, right? So here's memory address 0. I'm not even going to complicate it. And then, oh, that didn't work. And then we'll pop one down here, and we'll call this memory address 1, 2, 3, 4, 5, 6, 7. 7 or 8 things in here? 1, 2, 3, 4, 5, 6, 7. 8, right? Let's just call it those 4 things, right? Super simple. Now, this literally, internally, is split into equal chunks.
Yep.
Right? So literally each piece of memory is the same size because it's always the same type, right? And hopefully I did this right. So I'm going to start from the back. 10, 3, 8, 7, 6, 4, 1, 6. Okay, so 1, 4. I'm writing with my mouse, so excuse my handwriting. 7, 8, 3, 10, right? These are all equal in length internally. So this is really important, right? Again, this seems arbitrary. This seems like just a normal detail, but all of the things that are true right now that we're talking about will not be true later. And it's very important to understand when this is true and when this isn't true. So not only are they predetermined with a fixed size, each element is the same size, right? Which means the literal memory stamp of an array is fixed, right? Whether you want it to be or not, this array exists, and it is exactly the size, and this is how much memory it's taken. We're less defining these as this is always exactly the case, and more defining these as understand that these concepts of how much memory something takes up, whether or not size is fixed, and really like what typing you can have, will all be important later, and may not be true later. So this is pretty much all we need to understand at a core level about arrays. So now let's give some very, very basic conversation to just how we go through them.
So is the only difference between an array and a list is that a list can be expanded every time you append something new to it?
Yes, we will.
With the memory allocation?
Yeah, so we'll talk about linked lists, but they end up being actually very different in implementation, and you'll see that once we hit that.
But isn't there a difference between just like normal, like, because you know how you said arrays are memories allocated upon,
initialization?
Whenever you yeah, exactly. But in Python per se, right? An array is a list because you can append things, and the memory allocation of that array can expand every time you append a new item to it. No?
Right. So what you're doing there is, so there's two different things that can be, right? Some arrays are internally implemented where when you add more stuff, it'll make a new array, drop in all the old elements, drop in the new element, and then give you the new array, right? So the original array didn't actually change size, they just gave you a new one. Or it's a linked list, or a list like we talked about earlier, which is a completely different structure that we'll understand when we get there. So those are basically the two options. So basically, it's lying to you no matter what. it's either a different structure entirely, or they're actually just making a new array. Let's copy our array from here, right? Yeah, and like I said, don't get too caught up in all of the details of everything that I'm going to say here. A lot of it is a little oversimplified just for understanding's sake. So not all of these are absolute statements for every single language. Every language works differently, exactly how stuff is stored. Sometimes there's extra space, metadata, blah, blah, blah. But focus on the core concepts. That arrays are pretty much going to be fixed in size, and they're pretty much always going to be the same memory size, right? Because this is what's allocated. This whole brick is allocated min 1. Now, let's talk about questions we can ask, right? Or how many items are in here, right? And then, is 12 in the list? Now, programmatically, right? You look at this array, and you have to answer these two relatively simple questions, right? So, to answer the first question, what would you have to do?
You probably have to iterate through the array.
Yes, right?
And keep a counter of it.
Correct. Now, that's literally either that or the array internally stores it, whatever. But if you're just given this array with no other magic, yes, iterate through. Must check every item, right? Let's just assume that. Now, if I ask you, is 12 in the list? How are you going to answer that question? Oh, well, I shouldn't say list.
Yeah, so to check if 12 is in this array, I'd make a counter, put a hash, and then iterate through the array, and then put each value in the hash, and then compare if any values in the hash is 12, or you could just do like a straight comparison, but
assume that you have
faster.
nothing
Not
else,
too sure.
right? So don't try and answer the question optimally.
Okay.
Say this is literally the only thing you get. You get the array and no other memory space. How can you answer the question just looking at the array? Even if it's less efficient.
And yeah, just iterate through it and compare each value to if for our target of 12.
Just iterate through it, right? For different questions, you can implement different structures, but for the sake of this, we always want to understand how these structures are optimized for this. And the answer is, an array is not optimized to answer these questions, right? You still have to go through every single element here if you want to answer these questions. So very clearly, arrays are not optimized for the speed of answering these, but they are very exact in size, which ends up being helpful in a lot of other cases. That's basically all I want to call out. Just recognize that arrays are not very much optimized for searching, which is what this is. Yeah. There's no real great way to do that. But there are better algorithms that you can do. And I will just acknowledge that you can always do a binary search.
Binary search. Yeah. Classic.
Yeah. Which is
binary
the other default.
Search.
Yeah. And technically you can do it faster, but again, the structure doesn't help you out. Right? So, let's take this a step further, and let's start talking about lists. Now, I'm going to specifically call out lists as linked lists, just to be very clear. Right? So, a linked list is very different from an array, because a linked list has many more details, or many more specifications about size. So, let's take this guy. Oh my god. Bring it down here. And now let's see what's the same and what's different for a list, right? For argument's sake, let's assume that all of the types stay the same, right? So the element is a node containing any object. The size is undetermined. It can change size. Mm-hmm. Each element is... You don't really care about this, but let's just say probably same size because we don't really care. But we have no fixed memory state, right? We have no idea how big this is going to be. So the basic node, right? And I'm going to do this in like a JavaScript context because I assume that that's preferred language, right?
No, Python.
Python, cool. I don't know Python, so I'm going to do JavaScript anyway. Or at least we'll use a JSON notation. Assuming that you're familiar with how JSON looks. Like if I write just something like field type and what it looks like, right? So this node is literally going to have two things. It's going to have a data of, I don't know, let's just call it a string. Or, yeah, it's going to have a string data. And it's going to have a node, next, right? And that's it. These are the only two pieces of data any node has, right? And the way that this is generally represented, and I think they have shapes. So, right, you've got this node, and you know what, we'll even make this just an integer to make it easier, right?
Okay.
So now if we were to represent the same set of numbers here in a list, so we'd have a node representing 1, right?
Mm-hmm.
And that node, come on. This is going to look really nice at the end. It will be worth it. Points to, right, the node that has 4, right? Right, so this node in particular can be represented as data 1. Next is the node that holds 4. Right? And that's literally it. So as long as you have these two things, your list can literally be infinite. Because now let's look at 4, right? The way that we've defined 4 right now, it has a data of 4 and a next of null. So like these are our kind of two pieces of data here. Now if I want to add another one to the end here, paste my arrow, right? Poorly. And I can just give myself another new node, right? And I can make these nodes forever. And this one will hold 6, right? And so now what I've changed there, in just building this list very simply, is that the data here becomes 6. This one has a next of null, but now this one has a next of that node, right? And in this super, super simple insert pattern, I can literally go forever, right? I can always add another one, right? So if I ask you, how big is this going to be? You have to ask me, well, what the hell are you going to give me? Because I have no flipping clue, right? With an array from day one, you said this array is 10 big, right? Like you defined that memory size. The array was always going to be this big. But with this list, you can add forever, right? Now, when you actually think about how this is stored in memory, it's very different. Because now what you have is random blocks scattered throughout memory. And each one points to the next.
Why are they random?
So basically, whenever you say new node, you grab more memory, right? So every time you add something to the list, you're making a new object somewhere. You don't really care where. With an array, all of your memory is taken at once, right? So it's all contiguous. And this makes it super fast to loop through an array. But when you actually want to loop through a node, you're constantly jumping through memory, right? So this actually ends up being a lot slower for a lot of computers because you're not just going straight down. And computers are built to go like this, right? So when you can use an array, it's better to, right? When you can't, or when you don't know how much data you'll have, you want to use a list like this, right? Now, let's take this a step further, and let's talk about these actual operations on this list, right? Linked list operations, right? So let's grab this guy again. Oop, don't want to draw. Paste them into here, right? So now, let's talk about what we've done here, right? So if I want to add an element, what do I need to do?
Like a completely new element, like that, like let's say node 7.
Yes.
Well, I guess the first thing you do would be like declare it, so allocate a random space in memory for node 7, and then you'd have to add it to. It depends on where you want to add it, though.
Mm-hmm. Keep going.
Right? Because like that's the difference between stacks and queues. If you want to add it to the beginning, that's like first in. It'd be first in, first out, I believe. But if you want to add it to the bottom, it would be last in, last out, or maybe I'm jumping ahead there, but
No, but that's good, right? What you're discovering is why a lot of stacks and queues are actually implemented as linked lists, because it is just that easy, right? So generally, there are two main things that you have. You have a head and you have a tail, and you keep track
Right.
of these always, right? So generally, when I want to give you the list, I can either give you just the head and then force you to go all the way through the list to add to the end if you wanted to, or I can
Right.
have a separate object that is actually just containing the head and the tail. And then you can pick, right? And now, think through this, right?
okay.
Every time you add something, like let's say you add something to the beginning, what do you have to change?
If you add something to the beginning, then your head, you have to first link what was head previously to be the next of the new head.
Like new element to previous head. And now in this example, where I kind of have this concept of a head and this concept of a tail, what is now the head?
Yeah. Data 1, the first node.
So data 1 is the head now. If I added 7 to the beginning,
Yep.
what's the new head?
7.
Right. So if you add it to the beginning, then you have to link the new element to the previous head and then update the head, right? Now if you add it to the end, what do you have to do?
I have to change the tail.
Right. So you're going to update the tail, and then what do you actually have to do here, right? So we have 6 with a next of null, and I want to add this other guy.
Yep. Yeah, so if you want to add an other guy, your next would be 7, if we're going to still use 7 as the example. So your next would be 7, and then on your 7th node, your next would be null.
Beautiful. And what we're talking about right now is literally the basics of linked list insertion and yeah, just storage, right? And this is huge, right? This seems simple. But when you go to implement a linked list, recognizing that you have to do these things are very important, right? So you have to update the tail and set new node as old tail.
Oh.
Next.
That's actually a good comment by Math and Code. So he's saying you can do list.append, but is that necessarily true? Can you just append to a, like, 'cause- okay, so for Python, I'm not too sure how it works in like maybe more granular programming language, but for Python, there is a bit of a distinction between lists and linked lists, right? So in Python, you'd use something called a deck from collections, and you can use the append method. Or like what I've done was I actually created my own linked list class, and instead of having the append, I would do something where I'd iterate through every node, and then add it to where it would go into, the next iteration is none or null, and then at that slot, I would add it to the chain.
Right. So, what you've just described, right, is the key to what we're doing here, right? Recognize that what we're actually talking about is the behind the scenes, right? What we're actually looking at is we know that these guys have these functions, right? Like we know that lists in most languages have an append, have a prepend, but how do they do it, right? What does that actually look like? And that's the stuff that you're going to get asked, right? We talk about these structures because they are used to solve problems commonly had. And so understanding how they work internally lets you have the power to build your own and customize later. All right, so now I want to talk about one more thing, right? So what we've just done, and I'm going to give it some now more official words, right? At the beginning is prepend, right? Put it at the start. Add it to the end is append. And there's one last thing I want to talk about, which is add in the middle. Add an index, which is insert. So, looking at this structure, how would you go about inserting into this list, right? So I tell you that I want to put this brand new node that I just made, that is 50, and I want it right in between 4 and 6. I want it at index 2.
Okay. So my implementation would be you'd have like a temporary counter or a temporary kind of, I don't know, like, yeah, a temporary variable that is one step behind your main loop iteration that stores the previous node. So when you get to the node that you want to append 52, your previous node would be the previous node would be 4, and then you're changing the property of node 4 dot next to be the property of node 50 dot data, and then for the property of node 50 dot next, you'd be creating you'd be assigning that property to the value of node 6 dot data. That was a lot to say, but was it kind of correct?
That is exactly it. And so I've written that out in kind
Nice.
of like a pseudocode way here, which I don't know how to make the box bigger, but basically, right, so you iterate through storing current and previous node. When you get to the correct node, change previous dot next to point to the new guy, right? So we get to here, and we're going to change this arrow to go, oh, here we go, that way, right? And then we're going to set 50 to point down here. And that's literally it, right? And now you've got it. And now it's in that index. Easy enough, hopefully. Oh, that's not hello.
Oh,
Hello. All right, cool. Well, that ended up being where I wanted it to be, so that's good. Oh yeah, here we go. Yeah. So, insert, add to the end, add to the beginning. The last thing, delete. So,
okay.
how would you, now that you've put in 50, starting from the beginning,
Yep.
delete?
Deleting is actually easier than appending in the middle of the linked list, in my opinion, because all I've learned from linked lists is the only thing you're actually changing are those next properties, the links, the chain links, if you will, right? So if you want to remove like a certain node, like for instance 50, what we actually be doing is modifying the properties of node 4 and 6. And on 4, we're modifying the next property to just point, instead of the data of node 50, to point instead to the data of node 6. That would essentially like already kind of practically remove node 50, but then on node 50 we can also remove the property its own next property, or maybe we keep it. I'm not too sure. Can you just get by just changing the property of node 4?
So technically yes, but to get a little too big brain for this conversation, if you leave it pointing, it's bad because the computer will still think it's doing stuff.
Okay.
So the computer will not throw out that data or free it up. So you want to remove that. So
Okay.
previous dot next to point to the next node, and then you want to remove deleted dot next. Or set it to null.
Remove like current node next or something, right? That current node is the node that you want to remove.
Yeah. Easy enough. Cool. That's pretty much always free, boys. There you go. See, Zero Nerd called it out, right? If you don't free it, well, in modern languages, it should clean up for you. But seeing stuff still pointing, bad news bears. So making sure that you not only move this arrow to point here. Oh, come on. But also delete this arrow. Super important. And just like that, right? In each of these, just in plain English, we have defined every algorithm that relates to very basic linked lists, right? Cool. So, let's build up. Here we go. What do we got next? That was lists. Let's talk about stacks and queues just a little bit. So, get ready for everybody's two favorite terms in the world, LIFO and FIFO, which stand for last in, first out, and first in, first out, right? So, let's start here. Before I even get into it, which one's a stack, which one's a queue?
The stack is LIFO. The LIFO is a queue?
I'll put it to you this way. Define a Pringles can. Is a Pringles can last in, first
Stack.
out? Okay. And now is a Pringles can the last chip you put in, the first one you take out? Or is the first chip you put in the first chip you take
It's
out?
a great analogy.
Yeah.
It's a great analogy.
That.
Yeah.
People say like, oh, it's a stack of plates. I'm like, nah, it's a Pringles can. Because Pringles cans, you're actually limited, right? So.
Yeah, so it would be LIFO.
Yep. So, the last chip you put into the Pringles can, the first chip that you take out. For a Q, this is the grocery store. First person online gets to go up first. Simple as that, right? Now, we're going to actually draw these, right? So we're going to have a list of operations, right? So this is generally how you do it. Add 3, add 5, add 8, pop, add 7, add 2, pop, add 4, pop, pop, pop. Throw a pop in there. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. There we go. Now, let's build ourselves a stack. So, here is your Pringles can.
Nice.
Can't even spell Pringles. So, these are your operations in order top to bottom. Now, let's look at this stack, and I want you to tell me exactly what to do and where to put it. So,
okay, sure.
Go ahead.
Starting from the top. Yep, starting from the top. So we'll add integer 3 to the bottom.
Yep. So 3 comes in, falls to the bottom. Boop, right there.
Yep. Same thing with 5 and 8.
5 comes in above. 8 comes in above.
Yep. Yep. And then the pop, it's we'd have to remove the last operation or last thing we added into our Pringles can. So we'd be actually removing 8 because that was the last thing we added in. 8 gets popped off.
So you pop from the top, right? So 8 comes out. Nice. Keep going.
Yep. We add 7, that comes from the top to the bottom, and then for the next operation we pop it. So same thing we did with 8, we put it in, and then we can remove it.
So you add 7, and then it calls pop, takes from the top. Easy.
Yep. Same thing with 2, so we add 2, so it comes in from the top to the bottom. And then we pop it, since it's also the last thing we added into our Pringles can.
Easy.
Last thing we do is well, not the last thing, but the last thing we add is an integer 4, so we add that in, top to our Pringles can. And then we do pop, so the first pop removes that 4. The second pop removes the 5, because in perspective, that was the last thing we added into our Pringles can.
Right.
And then last pop removed the...
Sorry. So now at that moment, 5 is the top, right?
Yeah.
Yep. Going.
And then last one pop just removes the, same thing we did with 5, the last thing on top, which just so happens to be the last item we have in our Pringles can.
And there you go. Right. So then our output. So just pretend that pop. So key things to know about how pop works. Pop. Remove top of stack. Right. Oh, no, I wanted to bold that. And that's what a pop is. And we'll even define it as, and print it, just for posterity and output it. So, notice, our array integers went in 3, 5, 8, 7, 2, 4, but they came out 8, 7, 2, 4, 5, 3. Because of the order of operations here, right? So we're adding and removing chips as we go. Now, can I move this over here safely? Yeah, okay, hold on. Put this over here. Grab this guy, we'll move this to the top right. And we'll put that there. Cool. Now, let's copy the set of instructions, hopefully without the stuff. Yep. And now we're going to make a queue.
Okay.
Delete all these guys. This software is so easy to use. I'm actually very impressed. Sorry. So we want boop, boop, and yep. Q. This is a grocery store. So we're gonna start giving them names. We're gonna have Dan in here. We're gonna have Strix in here. We're gonna have Rockstar in here. We'll have a Melky in here. We'll throw in who else is in here? Math's in here, and we'll throw a C Films in there. Boom. Those are just the last names that I saw. And mix it up a little bit to keep you on your toes. Throw that pop there. Easy enough.
Okay.
Boom. All right. So let me just make it clear. This is the entrance. This is the exit. Give some text there. Enter. Exit. Boom. Alright, so, Melky, it's up to you.
Okay. Alright, so first Dan comes into the queue from our grocery store.
Boom. Dan is in.
Yep. And then Strix comes in.
So this is harder with text. Strix, boom. Easy.
Yep. Now, since we got our first pop, the main difference between stack and queue is since Dan, you were the first one in, you'd be actually the one getting popped out. There you go. Yep. Then we add Rockstar. Oh, I guess you are Rockstar's Dan. My apologies.
Yeah, sorry. There's our friend Dan in the chat
Dubious
as
Dan.
well. Yes, we do have
Yep.
the name. Yeah, hold on. Sorry.
Only one leaks keys.
That's. Thank you. Output. There we go. So, Dan comes out, right? And so that's. We've added Dan, we've added Strix, and we popped one. Alright, what'd you say was next?
Then Rockstar comes in. And then we do the next pop. So Mr. Strix, he's out of the grocery line. He just exits because he was the first one in relative to you, to Rockstar and Strix. Keep it simple. And then Melky, yeah boy, shout out to Melky Dev, comes in the grocery store. Brand new bun down shirty bot. And then we pop Rockstar. He's out. He got all the stuff. He's exiting the grocery store. Then Mr. Math and Code comes in. Oh, I see what you did there with the two pops. Interesting.
Thank you.
Pops. So Melky Dev. I finished my grocery list. I can leave peacefully.
Boom. Out of the fridge. Easy.
Easy. And then C Films comes in because he forgot he needs to buy Pop Tarts from the grocery store, so he's making a last minute run.
Boom.
And then we have a pop. Math and Code is out.
Out comes Math and Code.
And then interestingly enough, the last pop, it would be the same effect as a stack because relative to what's left in the grocery store, it's only C Films.
Yeah.
So in that perspective, C Films was the first one in, and then he will also be the first one out. So C Films will be popped.
And there you go. Right? So now, let me move this just a little bit. So, notice, Dan, Strix, Rockstar, Melky, Math and Code, C Films. Dan, Strix, Rockstar, Melky, Math and Code, C Films. 872453 358724. And notice
Kind of everywhere there, eh?
yeah, so this one's everywhere, right? This one's in order. Now you would generally expect one to be forward and one to be backwards. That would make sense. But the key here is it doesn't matter when you remove from a queue because it's going off of the first thing you put in. So you can take out of a queue at any time, in and out, and it's always going to be deterministic in exactly what that output is, right? But
so Q is always ordered. Is it fair to say Q is always ordered in a way?
They are both always ordered, but no matter what you do to a queue, it will always have the same output after, like in terms of pops, effectively, right? You can't change it, right? Now with a stack, since you're taking out the last thing you put in, you are actively changing the element that gets put in, right? And that's kind of important to understand. So the queue, right, everything's in, straight back out, you have the order. With a stack, If you add everything and then remove all of it, you'll get it in reverse order. That's easy.
Yep.
But if you add and remove procedurally, you will not get a guaranteed order.
Okay.
So only guaranteed order if you pop everything at end. Ugh, jeez. And then we'll have guaranteed order pretty much always. I'm gonna say quotes always because depends, but pretty much every time. Everything's coming out in the same order unless you do some really weird stuff with implementation details. Cool. Now, let's look at implementation. Implementing stacks and queues. Cool. So, stack. First item comes in, first item out. Queue. First item comes in, last item to come out. Right? So let's go back and let's steal our node list here. Now let's see if there's anything that we can do. So I'm going to start you by saying, let's build from this linked list, right? Now how can we make this into a stack, right? So as a stack...
That's interesting.
What does pop do?
As a stack, it just pops the last entry in, I guess, our Pringles can. I want to keep using that analogy.
Mm-hmm.
It'll move the last entry into our, I don't know, into our data structure.
So, let's get back our terminology that we have for linked lists, right? We have two very powerful words. We have head, we have tail. So let's use those words.
Gotcha. Okay. So yeah, as a stack, pop will remove last in the head.
Boom. Now, what about as a queue?
As a queue, first in, first out. It would be the tail, because everything pretty much gets pre-appended to the queue, so it'd be the tail.
Now take a look at this. So as a stack, right? I first put in 1, then I put in 4, then I put in 6, then I put in 7. What should I take out?
Okay. 1.
As a stack.
Yeah.
So let's draw that really fast. I build my stack, right? I put in 1, I put in 4, I put in 6, I put in 7. What's the first thing out?
Oh, it'd be the 7.
Mm-hmm. But if it were a queue, what would it be?
Right? If that it'd be the 1.
Right. So is this correct?
No, it's the opposite.
It's the opposite. Super easy
Oh,
to
that's
get these mixed
deceiving.
up.
Okay.
Super easy to get them mixed
Yeah,
up.
that is. Okay, that's actually
Little big brain. Yeah. It
Yeah, for sure. That's a gotcha. That's a gotcha.
That's why you always draw things. We'll talk about that more later as we get towards the end. But draw everything forever, because pictures are easier to understand, right? Notice that this entire thing, no code. Even this, like, still pictures, right? English. Understand everything as English, do the code later, right? The key is that in an interview, they trust you to get to this point and then convert it to code. I trust you to convert it to code. I'm going to give you the English. Cool. That's literally it. So literally, all of this linked list stuff, kind of complicated. Bunch of different stuff that we want to do, right? But if we want to convert that into a structure, you add one method. Literally just pop. And all it does is this. Right? And I will clarify just a little bit that you have to set the new tail. And that for this one, you do have to set the new head. Those are the only two little adjustments, which are just very specific, but conceptually, that's literally all you're doing, right? It's almost crazy how simple it is to implement these structures once you have the linked list base. All make sense? Everybody cool? Thumbs up in the chat if we're getting it while I take a sip of water. You good, Melky?
I'm good. That last piece was very helpful. Yeah, that last piece was very helpful.
Drawing. Pictures are wild. Oh, thank you, Math. Oh, that's so kind of you. I appreciate that. All right, we're getting a lot of thumbs up. I want you to know now. I'm gonna say this. This is gonna be where stuff starts taking off a little bit. It's gonna get a little bit more complicated, just a little bit. Then it's gonna get quite a bit more complicated, and then we're gonna get into algorithms, which are gonna be more coding-ish, and then we're gonna really jump. So be prepared. That this is like the small jump. Like this is the first hop in difficulty. Everything up until now I would call like truly basic, and now we're gonna get into like still basic, but a little bit more specific. So. Just so everybody has that context. So that's more of a way to say it's okay if it takes you another extra second to understand these. It's okay to ask more questions here. It's going to get a little bit less easy.
You're scaring me, Dan.
Oh, no. This is like, we're literally just going to talk about like trees, right? If you understand linked lists, you should understand trees. But there's more ways to move through a tree where you have to understand recursion just a little bit. So it's pretty...
I've never done trees yet. That's the next chapter. That's the next chapter in cracking the coding interview for me. So this would be my first real official data structure knowledge on trees.
We will imbue the body and energy of Mr. Beast, and in this moment, grow trees on stream. Now, here's what we're going to talk about. Actually, let me get rid of these for just a second. We'll bring these back in a second, but what I do want is just one of these guys. So, here's the difference with a tree. It's literally a linked list, but it has 2 next nodes. And you look top to bottom instead. So, let's get back to our shapes. Right? Wait for this guy to load. Pull this in. Alright, so. Super simple. Same stuff we were doing with a linked list, but instead of having a next, we have what we call children. And as with any good God-loving country, you are allowed to have at most 2 children. So, we do the same thing for our data structures. So, come on, move. Move. Oh, God, please. Oh, you have to do this thing. Oh? Hello? I think it's mad that it has more than one arrow pointing to it at once.
Uh-oh.
Oh, no, it's just... Okay. Well, I won't pretend to understand exactly, but here's the basic idea. Oh, yeah, right. Okay, so let's be clear. Before we start talking about... So trees in general can have any number of children, right? Just like in every other country, right? So, like, let's call them American trees, right? There are all different types of American families and American trees, and they can have any number of children, right? So in that context, where we might still have the data be 7 or something, instead of having a single next, we can have, children that's just an array of nodes, right? So instead of 1, you have many, and they basically just point different ways, right? So it's just like with the linked list, but imagine there's just a lot of arrows coming out, right? So 7 can point to any number where it could be. Thank you for the save, Strix. To 4 and to 2, right? Then we can. Yo, what? Oh, that just gave me a heart attack. Oh, thank you, Kiwi. I appreciate that. Thank you so much, bud. That's super nice of you. It means a lot. Oh, hold on.
Big shout out to the Kiwi Fruit Bird supporting Dan. Big shout out to the Kiwi man.
Yeah, Kiwi's one of our biggest supporters. Kiwi always comes through with the memes in Discord. We really appreciate it.
Let's go!
Yeah, let's go. So you can see here, right, in like a super random arbitrary tree, like this is valid, right? So like 7 has 2 children, 2 has at least 1 child, right? So it's an array, right? Or let's use correct terms. It is a list of nodes, right? Because we don't know the size. So, and it's just that simple. And so the basic idea is this just gives you a top-down view, where you still have a head, but that head now points multiple directions. So you don't have a tail anymore. So now the terminology here goes from, instead of head and tail, head becomes root, and tail becomes leaf, right? You can only have one root, you can have many leaves. So this is the start of the tree coming down. Simple enough, right? So, doesn't seem like it does too much. Don't worry about it too much, but just remember, the arrows only go one way. Now, there's a whole lot of kinds of trees, right? And arguably, I can add these guys forever wherever I want them. And it can be same data, different data, what the heck ever. But there's one kind of tree that most people talk about. So I'm not going to spend too long worrying about this, but understand in the same context as what we were talking about. Oh god, hold on, my music's getting weird. I need to make you disappear for a half a second while I restart the playlist. There we go. Back to Megalovania. God bless America.
God bless America.
Cool. So, calling this out, can you tell me which one is the root and which ones are the leaves?
Well, the root is definitely going to be that 7, I believe. It's kind of hard to see because I see the red dot on my screen. But yeah, it would be the 7. That would be the root. And the leaves would be all 2, 4, 4, and 3.
So, allow me to define slightly more. So the root, move it over. Root has no parent. Oh, hold on.
Okay.
So it's an orphan, right?
Oh, yeah.
But a leaf, come on, has no children.
Oh, okay. Okay, so the head, it's still 7.
Use the remember we have
and the
new terms,
leaves
right?
are-
So it's not a head. It's a root for this one. This will be important later.
The root would be 7.
Yep.
Root would be node 7. And then the leaves would be node 3, node 4, and node 4.
Go. Leaf. 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 Boom. So, basic structure, basic language. Why is the tree upside down with the root on top and the leaves down below? That's the biggest meme in programming. We draw our trees upside down. Welcome to data structures. Yeah, Australian trees. There you go. Beautiful.
That is so good.
So, that's just the basic concept of a tree. But we're going to talk about the most popular form of tree, which is the binary search tree, or BST. So now, a binary search tree is a tree where each node has at most 2 children. Now, as I explained to you what a binary search tree is, I want you to keep in mind the binary search algorithm that we've talked about in the past. In general.
Okay.
I'm assuming you have some familiarity with it, but
Yep.
if not, it's okay because the structure will kind of explain it. So let's go back and let's
good.
copy. Right. So pulling from here now, let's bring these back in. So the key with a binary search tree is it is exactly that. It is binary, which means you can have at most 2 children. Is there a name for the nodes that are not roots or leaves? Not really. You could probably find something, but otherwise you could just use general data structure like language. So you can call them just nodes in general, or you can just call them elements. But as you get into more and more complicated algorithms, you do start saying stuff like parent, grandparent, and like child, grandchild. It's actually pretty funny. So now instead of a list of nodes, right, we actually know exactly how many children we're going to have, right? It's 2. And in particular, because of the way that we draw it, generally, the way that we do this is that we actually just write it as a left and a right child. Because that is, quite literally, as we draw it, how it's pictured. Does that make sense?
Yep.
Cool. So, for 7, right, this is going to be the left. This is going to be the right. And now 2, this is going to be the left. Oh, did that pick up? Left. Right? So now very quickly, let's just draw these out real fast, right? So for 7,
Okay.
For a root, what does our data look like? What's our data? What's our left? What's our right?
For the root, so the root is node 7.
Okay, so what's the data?
Oh well, that's actually, yeah, the data is 7.
Good.
The left is node 2. And the right is node 4.
Great. Now let's talk about it for this guy.
So then that would be a leaf. No. So for node 2, would it be a root?
No,
It wouldn't
so
be because it has a parent, right? So what would you call that? Just node 2?
it has no good name. That's what we just acknowledged with math and code. We don't really have
Okay.
a good name for it, but it's a node. It's an element. It's just a regular old node.
So then regular old node 2, the data is 2, left is 3, or node 3, and then the right is null, or none.
Good. Perfect. Right? So understand when it's not there, it's null. That was all I hope to get out of that. You got it, nice and easy. Right? And so that's the basic idea, is all of these values are either, for left and right, it's either a node or it's a null. And those are the only two things. So if I asked you now, what does every leaf look like? We don't know the data, but can you tell me what the other values are?
In a leaf for the left and node,
left
for the
and right.
left and right properties,
Yeah,
I'm assuming there'd be both nulls.
right. A leaf has no children. So when you want to programmatically find
Exactly.
out if something's a leaf, you look at the left, you look at the right. Yeah. Basic data structures. Binary search tree. So that's the thing. With trees, you always have to keep adding to the definition. So now let's take this same thing, right? Copy most of what we've said here. But we're going to add one rule. A binary search tree
What's the rule?
is a tree where each node has at most 2 children. I'm going to write these as bullet points because there's technically 3 rules. Each node has at most 2 children. The left child is less than the parent. The right child is more, or is greater than the parent. Less than, oh wait, I already had the than. Now this is referencing data, right? So let's throw this into the corner here. Alright, so, now, first question. Based on just these rules, is this a binary search tree?
The thing that is throwing me off is the bottom two. The saying the left child is definitively less than the parent, and the right is definitively. Well, no. In a binary search tree, you'd actually set the order first, so you have all elements ordered from like small to biggest. And so, in binary search, you start from the middle value, and then left
So-
would be less
Don't overthink it,
than the
right?
parent. Yeah, I'd say this is a binary search tree.
Alright, so, our top value is 7. Is the
Yep.
left child of this less than the parent?
Oh. Gotcha. Sorry, I wasn't. Is the left node at? Is the left child less than the parent? Yes, it is. 2 is less than 7.
Great. Is the right child greater than the parent?
4 is not greater than 7.
So is this a binary search tree?
It is not.
It is not. It is a binary tree because it only has 2 children, but it is not a binary search tree, right? Super common question. That's a weirdly common thing that they will ask. It's just, is this a binary search tree? Now, I'm going to update this to 15. Is this a binary search tree? The whole thing.
2 is less than 7. That's correct. 15 is greater than 7. That is correct. The thing that's throwing me off is the left node there, because then 2, you have to compare with its left node, and 3 is not less than 2. So, you know what? I'm gonna go with no.
All right, and why no?
Well, so the first, if we only look at node 7, 2, and 15, I would say yes. Then because node 3 branches from node 2, I'm kind of switching the definition, right? I'm looking at 2 as our kind of root, and then look and saying, is 3 less than the parent, which is 2, and that's no. So by that, it breaks the definition.
Good, right? So the key here is this says each node, right? So you don't have to think about it like each one's the root. Just every node is a parent to some number of children, or it's a leaf.
Gotcha.
Right? So
Yeah.
that's the hard part. So sometimes a really tough question is go through a tree, a binary tree, and figure out if that binary tree is a binary search tree, right? And so that starts to get a little complicated, right? Because you answered that question looking at it, but can you answer that question programmatically, right? So I'm actually going to give you a few more tools before I ask you that question, but know that that question is coming up. All right, we're about to get into actually some a little bit heavier stuff. We're about to start talking about recursion, and we're about to start talking about tree traversals. This is going to take a minute. Binary. Let's just talk about... We're going to hop for a second. We're going to talk about basic algorithms, and we're just going to talk about recursion as a concept. This one's going to get a little bit more code heavy. Just a little bit. But this needs to be understood before we can get into how you can use binary search trees. So I don't want to assume that anybody understands this. So, recursion. The old joke is the definition of recursion is recursion. In programming...
Dan, can you try to make the font a little bit bigger?
Yeah. Oh, it got small again, didn't it? Yeah.
Yeah.
Boop. Oh. Cool. Boom. Add some girth to the font. This programming, recursion is a function that calls itself. So, let's give ourselves some fake code. Function, whatever, takes an int, takes nothing. And inside the function, we call whatever. Ah, yeah, that's the old meme. To understand recursion, one must first understand recursion. Right? This is the most basic recursion ever. Right? What happens if I call the whatever function?
You just call the whatever function again.
Correct. And then what happens?
Which calls the whatever function.
And then?
Which calls the whatever function.
And after...
And then calls the whatever function.
Repeat ad infinitum, and eventually we get the legendary error. Stack Overflow. Basically, the reason this happens is you've made an infinite loop of calling... Oh wait, I can change the text color to be red. Boom. So, if whatever calls whatever, or we could even change it to be forever calls forever, it will run forever. But forever is defined as until your program literally crashes. Which will happen, right? And the error you will get will be Stack Overflow. And I can explain why that is if people actually care. We can get into that a little bit later. But, in general, this is the wrong way to do recursion. So, what this calls out is the need for the one core function of recursion, which is a base case. The end of recursion, the point at which recursion stops. Oh, that's not what I wanted to do. That is. Right? So, understanding a base case. So let's update our forever. Let's give it a base case. Right? This is going to take an int x. We're going to say if x equals 1, return true. And we're going to call forever on x minus 1. And now somewhere else in my main, I'm going to call forever 15. Now, boom. What happens?
Wait, forever. So if you call forever 15, well, did you update? Do you need to update the forever function?
Sorry, the not forever function now.
There you go. Okay.
Yeah,
okay.
there we go. Sorry about that.
All right. Let's say if it's so you're passing 15 into the not forever function. If x equals 1, which is not the case, passing 15 not forever x minus 1. So it goes 15 and then reduces the int value by 1 every recursion until we hit 1. So that's what 14 times I believe, or 15 times, and then it exits the loop. So it basically it essentially hits itself 15 times and then it exits.
Boom.
Yep.
And just like that, that's recursion. That's literally it, right? All we have to do is add a base case and make sure that we give some functionality that ends eventually, and this will complete. Now, very quickly, I'm going to call out something that's really important to understand about recursion, which is the dark side of recursion. This is what is called...
Dark side of recursion?
Correct. This is what is called the call stack. And I'm even going to capitalize this. Right? And so the idea of the call stack... Can I make this bigger? Can I move this line? Sorry, we got to make more space. Even in virtual whiteboards, I run out of space. Alright, so... Alright, so this is a call stack, right? What I'm about to say is going to sound kind of complicated, but it's very important to understand. Every time you call a function, it stores some data, right? When you call not forever 15, it remembers what x is, right? And when not forever 15 calls not forever 14, not forever 14 also remembers what its x is, right? So let's think about this in memory,
Okay.
right? This guy's storing its own x, and maybe it's only really tiny, right? But then this guy's also going to store its x. And this one's going to store its x, all the way down to this one storing its x, and this one's storing its x, right? And so what ends up happening is that you actually take up more and more memory all at once the more you recurse before you return. Now, I told you earlier you were going to get this error. Stack overflow. What does that literally mean? Memory is literally stored in a stack data structure. And when you loop forever, you don't finish this. When you call the forever function, you just make one little square at a time, over and over and over and over and over and over, until you literally fill up all of your memory, which happens to be stored in a stack. And the stack runs out and literally overflows. So when you get recursion wrong, your stack will overflow.
Yep.
The term for those, in particular, we call this the call stack because it is a stack of called functions, right? Now, let's also think about this very literally. Each function I've called, right? What did I call first? I called not forever 15, right? So the first one I call is 15. Then I call not forever 14. And then I call not forever 13.
Yeah.
Then I call all the way up not forever 2, not forever 1. Right? And then it returns. So which function returns first? Right? 15 can't return until 14 returns because it's waiting for this to run. Right? And 14 can't return until 13 returns.
Oh, so that's like last in, first out. That's LIFO, right?
Exactly. It's a
if
stack.
you look at so then it's a stack. So then the first one to be returned is 1.
Exactly. And then once 1 returns, what comes next?
2 gets returned.
Boom. All the way up. All the way up through 13, 14, and 15. And that's why we call it a call stack. Because it is quite literally a stack of function calls waiting to return. And they even have memory, right? So it's a stack in every single way. Now, when people talk about the phrase iteration versus recursion, this is the only thing you need to understand. If I did a for loop, I wouldn't have a call stack. But if I do recursion, I do. So if anyone ever asks you the legendary question of iteration versus recursion, the answer basically is call stack, bad. That's literally it. Right? That's literally it.
Yep.
When you iterate, you'll never have a call stack. Wish I could give Dan the 300. I always saw data structures and algorithms class. I took at Uni. Aw, thank you, Strix. This is your own personal education.
Real.
Hey, and this was a sub goal. So this is because you guys have been so supportive that I'm able to do this. Basically, the idea is with each of these, right? I said that they took up their own memory, and so 15 is like basically saying, hold on, let me do text here. So 15 is basically saying return 14. And then 14 is basically saying return 13, right? And then so on and so forth all the way up. But when you do tail call recursion, instead of these each taking up new memory, it basically understands that 14 is just going to 13, and it replaces the 14 with the 13, right? And then it replaces the 13 with the 12. All right, so I'm going to give you a slightly better example so that I can talk about how tail call seems to work based on me just reading a single Stack Overflow page.
There you go.
Return x times factorial x minus 1. So basically, the idea here is you're familiar with the factorial math, right? 5 factorial equals 5 times 4 times 3. Oh, I didn't hit shift.
3
times 4
2 times 1
times 2 times 1. Boom. Easy. Right? Now, if we wanted to do this recursively, this is what that function would look like. Right? And so, hold on. Give ourselves more space. Right? If x is 1, return 1. If it's greater, return x times factorial of 1 less. So it's the same idea, right?
Yep.
Factorial of 5 returns 5 times factorial of 4. Factorial of 4 returns 4 times factorial of 3. Right? So on and so forth. And so now, let's just call it fact, right? Fact 5 equals fact 4 equals 5 times f of 4. And then f of 4 equals 5 times f of 3, right? And then f of 3 equals 5 times f of 2, etc., right? That's the basic idea of how that factorial works. Now, the problem here is these are each different little blocks in memory, right? The way that we normally store it. We've got this one, we've got this one, we've got this one. Right? Now, with tail recursion, what it'll actually do is understand, like, oh wait, I wrote 5 every time, sorry. 4, 3. It builds one formula as it goes. So instead of saying 5 is this, and 4 is this, and 3 is this, and then return, what it'll actually do is it'll basically just say, it kind of just tries to track an answer, right? And so at the highest level, it says answer equals 5. What was that? Yo, Astro! Thank you for the sub, man. Oh, I appreciate that so much. Thank you, bud.
Hey, Astro!
Ah, that's so nice of you. Thank you. Sorry, I'm trying to make this clear for people looking back later. So now if we add tail recursion, and remember, anybody correct me because this is literally based on a single Google. We start to do math for answer instead. So here we have answer is 5 times f of 4, right? But then as we get to the next line, it realizes that the answer is now developed into 5 times 4 times f of 3, right? One piece of math, right? One formula. Not a bunch, not storing all of these separately. One formula, that's that. And then we get a level lower. And it says, answer is 5 times 4 times 3 times f of 2. And then finally at f of 2, well, okay. Well, we'll work this one out just to be clear. It says 5 times 4 times 3 times 2 times f of 1. And finally we get, what was that? Dude, what? Oh, jeez. Thank you so much, Astro.
True.
Holy crap. Dude. Hi. You're cool too. Jeez. Oh, thank you so much. Wow, that was insanely kind of you. I was about to say that was insanely cry of you. Everyone, please stop saying the cry command every time something good happens, guys. Thank you, bud. Wow, that was wow. Thank you. I really appreciate that. Yeah. Wow.
Yeah, Astro's awesome. She's actually like a kid. Yeah, she watches Kid Boga, and she just started programming like I think a couple of weeks ago, and she's just absolute monster.
Oh my god, guys. Jewel, thank you. Holy crap. Oh.
Cry.
Yes, I'm not.
Cry.
I'm really
Dream,
not gonna
make him cry.
No, please don't do that. Please, I will cry. Like it will happen if you. But no, I don't want to cry on the interview stream, because then it will go in the VOD. Astro wants you to have nice teeth. Oh jeez, that one's not gonna happen. But wow, thank you both so much, Astro and Jewel. That was super kind of both of you. I appreciate you guys. Thank you for hanging out. Thank you for being a part of this. I do it because everybody's super cool. So thank you. It means a ton. Yeah, but basically for tail recursion, the idea is instead of storing all of these boxes, it's just one box. And the one box is always the same size, and it stores this at each time. And you're just replacing what the actual box is. So at the end, the box contains this. So basically, each of these is a box, but then it's just transferring the data. Or it's updating the data in the box. So it's kind of like a variable. Yeah, so the basic idea is instead of this terrible call stack, it's just one little variable that pops up. And then once you finally get the answer, it just goes straight from here, right up to f of 5, and returns it directly there, and just skips all these guys. Is there ever a reason to use recursion? Is iteration always better? We're about to talk about the best use for recursion. Well, the default use for recursion. Alright, cheers, Dane. Thank you so much for stopping by. Yeah, we'll be going for a while. This is my whole night, is the plan. We are teaching everything. So that's tail recursion. Some compilers will do that, but not always. So in general, just say call stack bad, depends on the language. Yeah. Cool. So, we understand trees, right? Let's go back and really quickly review this, right? We have any kind of tree, and we know that trees have children, a root, and leaves, right? Leaf has no children. The root has no parent, right? And it's the only node like that. Easy. Now, binary tree, right? It's just another tree, but it has only 2 children, right? So we say left and right instead of just an array, right? So we get to this level. Again, we still have our leaves, we still have our root, and finally a binary search tree with the magical rule that's the first one that actually talks about the data, right? Left child's less, right child's greater. Now, here comes the fun part. Basic data structures, BST traversals. Now, this is a classic thing that came through, right? So there are 3 ways to answer this question. And the question is, the task is print a binary search tree. So, if I give you a tree that is defined by the node, if I give you the root node, you get the root node. Nothing else. How do you print a tree? And I'm going to copy it down for you so you can look at it.
How do I print a tree? Okay, wait, hold on. So this is the tree I'm dealing with. So you gave me. You're not only giving me the root. Okay, so I got more
No,
than
no.
the root node.
Programming.
Or does this kind of...
Programming wise, I say, here's the root node, print the tree. Now you're looking at this, you know that this is what all the data is. I'm showing you this in like a picture so that you know if you're right.
Okay.
But at the end of the day, I give you
Right.
like literally the piece of data I hand to your function is going to be this. And it's just going to be for the root. And this is the data that you get. Data is 7. Left is the node 2. And the right is node of 15. And let's really quickly fix this. Boom. And then make this 1 so that it's valid.
So I would probably have to do some sort of...
So I didn't give you this, right?
Would it be... I'm trying to think... Would it be recursion here? I think it... yeah, I think it would be recursion. Because, so I'll start... Oh, wait, you know what?
Here's your function.
So I would say, if I start the root node, I'll do a recursion to look through each of my... and see if any of the children equal null or empty values.
Alright, I want you to write this.
But see, okay, hold on.
Write it in English if you'd like. Alright, are you ready for your code
A little
review?
nicer. Yeah, I'm just trying to format this because she's a, you know, it's a little ugly.
Oh yeah. We can
Okay.
here.
Well,
There you go.
there we go. So if no, then so if it's if no, the left and the right equal null, then what do I do? I just want to like exit, like return false, or else but no. Yeah, so I'll write something like this to start. Let's see where I'm going.
Sure. So let's take a look at it, right? So
Alright.
So right away, what is nodes, right?
It would be all the nodes in the tree.
Right. Do you have access to all the nodes in the tree?
Oh, you only gave me the root node.
I'm only giving you the root.
Okay. So if that's the case, but then okay. So if I only have the root and the root is an object, the properties wouldn't make root.left, root.right would be how it would access the properties of that root node. Then the question would be, how do I access the properties of those, like the nodes of that property?
Right.
Which would that would be the recursion aspect of it, right?
Yes. So let's start thinking about that, right? What is that? Nick suggests just use gotos. Do not do that. But let's
Okay.
talk about recursion, right? So
Okay. Well, let me delete everything then.
go ahead.
That's my attempt at it.
Yeah, no.
So-
it was a good start.
For node, the here. Okay, so for node, well, first of all, it would have to be a for loop, no?
Does it? Remember, the two options that we often talk about are iteration, which is a for loop, or recursion. Do you need to loop?
Okay.
Keep in mind the object you have on
Oh.
the top left here. This is your
Would the
example.
recursion be a while loop?
Would the recursion be a loop at all?
It doesn't have to be. It could be a function call, right?
Could be a function call. Remember, a recursion is defined as a
Okay,
function
so-
that calls itself.
Oh, okay, so then we have print tree node root. So we got past that. So the recursion aspect of it would be something like this. We'd have to call this with some sort of node parameter. That would be the recursion portion of this. Obviously, like as we discovered, we have to put a condition here. So an if something equals, I'm guessing it has to be none, right?
Yeah, let's say
And
null.
we return. Yeah, okay, so let's say null. So we have the condition that breaks our recursion, that returns null. This is the recursion aspect of it here.
And what is
It's
that
the
first line
recursive-
called, real fast? What's the name for that line that stops the recursion? Important
I don't
term.
know.
Scroll up. Top left. On page 12. This is a base case.
Oh, it's a base case? Okay.
That is the line to remember. So, when you finally return, that is a base case. Good job. Some people in chat got it.
Yeah, so
Keep going.
I was writing that down. Okay. So a base case returns out of a recursion. So then the thing that I need to struggle with is how to call print tree with the node. And I have to put in the condition of my if statement, right?
So, remember,
Um,
look at the object you have, right? You have a root that has its own data, it has a left, and it has a right.
Yep.
So go from there.
Right. If node root. Can I refer to it as just node?
Sorry, took my headphones off for a sec just to open the window.
Yeah. What can I refer to? Can I refer to the like? Because we call print tree. We're passing in the node root, and we pass root. I can just call it as node, correct?
It's a root is the name of the variable.
Okay, root is the name of the variable. Okay. That would be kind of confused. No, I don't have stage fright. I do not have stage fright. This is just
I can take you
I guess
through it if
challenging
you'd
for me.
like.
So, well, no. I kind of want to figure this one out. So one thing that I'm struggling with is the properties of left and right within the root. So I can have access to them, right? I can say root.left will give me the properties of node 2, and root.right will give me properties of the node 15.
Mm-hmm.
The thing that I'm struggling with. Oh, but then that's the recursive element of it.
Mm-hmm.
So what I'm thinking to do, let me do like a brute force approach here.
Yep.
So if root dot left, maybe like and root dot right. So if these two are true, would I then call it on itself? So if root dot left, okay, so here I'll do a brute force approach right now. You tell me where I'm going with this. So if root dot left and root dot right are both true, then what I want to call is print tree. Print tree on that root. So yeah, that would be the approach. It's definitely wrong here because this is the part where I'm kind of getting mixed up here. And this is even code. This is just me kind of blabbering out loud. Let me just delete this. So if you can help me out here, the first statement is if something is null. So let's see, if recursion is null. So if root dot left. So yeah, okay. So this is where I probably want some kind of a little bit of guidance here. Is properly allocating or getting that root node to pass into the recursive function.
So you're getting towards it, right? So let's say this, right? Where do you need to recurse, right? So like the tree can go infinitely in both directions, right?
Right.
So this tree
Yeah.
can keep going, right? So we definitely need to go all the way down the left and all the way down the right, always, right?
Yeah.
Good. So, can you split up what you've written into two separate versions? One for the left, one for the right?
Yeah, it'd be two separate if loops, right? Or if statements.
Go ahead, write it in. Yeah, sorry guys, my internet's kind of slow, so I think Milky's cam is dead for me at the moment.
We'll do if root dot left. This will handle all of our root left instances, right? So then if I'm following here, so if root dot left, I'm starting from node 7, I go here. Now I'm at node 2, right? So if root dot left is true, which in our diagram is correct, root dot I then have to do recursion on that node, on root dot left. So print, what is it? Print tree root dot left, and then follow the same pattern for this. If root dot right, following our diagram here, if root dot right that exists, which it does because that's node 15, we then have to call print tree on root dot right, and that'll be the recursive. That'll be the recursion on both the roots.
Great. Now, final question. When do you print?
Where to put? Yeah, the print statement, right? That's the next thing. Let me think. So if we find a root, okay. So first, would it be two print statements, one for each branch?
Put a print statement somewhere and then try and run it in your head.
Okay, so what it's telling me right now is I'll do this first. I put one here. Did you notice, by the way, you can't tab in these like text boxes?
Yeah, it's really annoying. But I mean, we're not trying.
Yeah, that is annoying.
They're text boxes, not code boxes, so I don't blame them.
True. Okay, so this. Okay, so in my head, we'll go through print tree, right, with our diagram. So if root dot left. Oh, actually, I skipped the base case. So the statement for the base case, empty or yeah, it would be if like no root.
Good.
So base
Good.
case, if our root is empty, so if there's nothing, so if it's just like child, I don't know, a leaf. If it's a leaf, there you go. That's proper terminology. Then we return out of function. If our root dot left has a node, we then print that node. So in this case, we'd print node 2, and then we recursively call it that node. So then we print tree on root dot left. So then we recall, I guess, print tree with node 2, and then do the same thing. And on the other side, we'll go into root dot right, which is node 15, and then we'll print that node. So we'll print 15 and then recall it with the print tree function.
Great. Now, if I give you 7, I start this, right? I start this. I give you the root. The root is the node 7.
Yeah.
When do you print 7?
Oh, that's oh, okay. So I actually don't need 2 print statements, because if we think about recursively, each node instance in the perspective of this function, every time you call it, the root becomes the node at which you are at. So it becomes the branch nodes. If we start at 7 and we go and recall print tree with the root dot left, the root becomes the second node. So then you can actually print it in the beginning of you calling this function. Okay, so that deformatted everything, but I'll probably just print node before you even go into anything.
Just to be clear, that's root.
That, yeah.
Yeah, thank you for the
Dude.
resub, CM. I appreciate it, bud.
Hey, what's up, CM Griffin?
Lurk mode. All right. Good. Very, very good. Good acknowledgement. You realize that the print statements, you only need the one. Now the final question. Are those lines all in the right order?
Are those lines all in the right order? Okay, so root dot left, root dot right, they're irrelevant. They can be in whichever. It doesn't matter which one's on top. So I guess your question is more pointed towards the print statement and the base case statement. I feel like the base case statement can go ahead of the branching node statement. So looking further, it will be the print statement, which is what you'd be challenging me on right now. Think about this before I just guess and randomly put it somewhere else. So we start the print tree function with our root node, right? So that would be can I draw on this, by the way?
Yeah, totally. Click the pencil.
Okay, so we start here with root tree. So no root is node 7. If we go down, if not root, if whoops, let me do that. If not root, that doesn't make sense. We need to print this thing. So we call the function, we print it. That's fine. Oh man, well, I don't know why that keeps happening. Wait, how did I draw this line?
You're probably lagging as you type it or something.
Okay.
So don't overthink it, right? There's
But
not.
I'm thinking it would be actually. I think it would be actually after the base case.
Why?
Because if we get past the base case, then we're confirming that we have a node that we can actually print.
That's it. Now finally, can we fix up that first line a little bit? Yo, thank you, Scooby.
Hey.
What's up, bud? Good to see you. Oh, and Mortal. Whoa, 2 at once. We're getting a lot of followers today. This is awesome. Thank you guys so much. Appreciate you guys stopping by. Melky is big, bro.
Yeah. So the base case here. See, the base case is what I was struggling with in the beginning too, because the base case is basically looking for a leaf node, right? Which, by nature, is a definition of if the left or dot right properties are null. So, is my base case really going to be checking for both those properties? That to me seems kind of, I don't know. Like, I don't know if that's the right way to do it. I'm saying, like, if no root dot left.
So let's back up before we get too low here, right? What you had earlier was very close, but you had if not root equals null, so you were kind of like double negating yourself, and so it got a little complicated.
True.
So let's go back to what you
if
had.
root equals null.
Good. Now, I'm gonna take a step back from this. Does this work? I want you to run this algorithm for me. I want you to look at this tree and run this algorithm. I'm gonna hand you the 7 node. What happens?
Okay, so
I want you to write out your output.
Okay.
Everybody watch this. The order of everything he's about to write is very important. You can do it in a text box, you can do it with pencil, whatever you want.
Okay, let me see. Okay. So first, we have 7. Root equals 7. If root, so if root, it's true. Because 7 does have a left and right. But see, okay, so hold on. Before I get into it, does my base case actually work?
You tell me. Or I can tell you.
I feel like for my base case, I should be at least accessing some properties to make sure that I'm at a leaf node.
Do you need to be at a leaf node? Is a leaf node
so
null?
let's say, okay, so is a leaf node null? No.
No, it's not.
The leaf nodes dot left and dot right properties are null.
Correct. So, does that mean?
But my base, I do have to modify my base case.
Do you? Think about recursion, right? Think about this process. I want you to literally, without thinking about the code anymore, run this code. I want to watch you run this code. And take a look at what you've written, and let's see it actually happen. So I'm going to hand you 7. What happens? First line. If root is null, return. Is the root null?
No.
Alright, great. So you're going to print...
We print 7.
Alright, so put it in the output. Great.
I guess I could just print 7.
Yeah.
There you go.
Great. Next line.
So then, if root dot left, That's true.
Okay.
We then go into print tree again recursively, and our root then becomes node 2. So we place node 2 into here.
Great.
Okay, so then we go all the way back up. Is 2 null? No. We continue. Print root, we print 2. Okay? Now we ask ourselves again, is root dot left? We look, it's true. We go over print tree once again. So now we're at node 1. We pass that as our root node. We go back. If root equals null, this is where but it's not null. Oh shit. Oh, okay. So then we put 1. So then our output is 1. Okay. If root dot left, that's not true. If root dot right, that's not true. So then what happens?
Tell me. You wrote the code.
We're at node 1. There is no root dot left. There is no root dot right. Can't really exit this. So I need to modify this code.
Do you though? Are you done? Have you finished running every function you've called?
No, I didn't go on the right side yet.
You haven't gone on the right side yet. Think about that call stack.
But how do I get out of this portion here? So I'm at node 1. Oh wait, if root dot left, which doesn't go, and then I go to root dot right, which also doesn't exist on node 1.
Okay, so you finished looking at 1. Now where do you go?
Yes.
Where
I have
are you
to
right now?
go all the way back up to. I'm on node 2.
You're on node 2, right? So what you've printed here, right,
Yeah.
your output right now, is actually also your call stack,
Okay.
right? So now you just finished 1. So now as is being recommended,
Yeah.
I'm going to give you a call stack here. So you've called
Wait,
7.
no, I didn't finish 1 because I didn't go on the right. I didn't go on the right side of 7 yet. I didn't do the 15.
Cross them out when you finish them. Ah, thank you so much, Totally. I appreciate that. That means a lot. Thank you, bud. Oh, and Callow got one. Sick. So, if there's no left and there's no right, what happens?
That's what I'm thinking. That like looking at my code, I don't understand what happened.
Alright, so then let's talk a little bit about... Oh my god. Wow, holy shit. Jesus Christ. Dude, Ghost. Thank you so much, man. Oh
Big
my
shout out
God.
to Indifferent Ghost.
Dude, Ghost is like... Ghost and Totally are like easily like 2 of my biggest supporters in here. I love you guys so much. Thank you, I really appreciate it. Thank
Hey,
you so
love you
much,
too.
Ghost. Oh, you guys are the best. Oh,
Hype
damn.
train.
There you go. Thank you, Jewel. Oh my gosh, you guys are the best. Oh. Oh my god. Thank you all. You guys are too kind. Alright, I want to write this a little bit differently. Right? So you've got 7,
Okay.
which has a left and a right. Right? And then you've got 2. Left. Right. Oh my god. Drawing is so hard. You guys are the best. I love you so much. Oh god. And then you have 1, which you call with a left and a right, right?
Yeah.
Now, have you finished looking at 1's left?
Well, yeah, it doesn't exist. So that I don't go into that if statement.
Okay, have you finished looking at 1's right?
It'd be the same thing. It doesn't exist. So yeah, I'd be finished looking both of them.
Boom. Now, we came in from 7, and where did we start looking? Oh, holy shit, guys. Dude, Scooby, thank you so much, man. Holy crap.
Okay.
Oh,
Then
God.
we'd go.
Jeez. That's so many. Oh my god. Dude, thank you all so much. Holy crap. Oh my god. Hold on, I'm sorry. I don't mean to interrupt. There's a whole lot happening. Oh my god.
Yeah. Do what you gotta do.
Thank you for the follow, gamer. Thank you so much, Scooby. Thank you so much, Totally. Yo, we hit level 5. Let's go! Oh, you guys are the best. Oh my god. Thank you all so much. I literally, my stream can't even keep up. Oh my god. This is insane. Oh my god. Come on. Jesus Christ. Thank you, Ghost. Oh my god. You guys are being way too nice. Oh jeez. Okay, hold on. Let's back up in this algorithm, right? So you ran 7, and oh my god, thank you, Space. Right? You ran 7, what was the first thing you did?
I looked to the left side.
Went to the left. Boom. You went through 2, what was the first thing you did?
What's your left side?
Great. Then you went to 1, what did you do?
There is no left or right side, so I'm finished.
Good, you're finished with 1. So where are you now?
I should be on the right side of 7.
No. Look at your stack. Where are you?
Should be on the right side of 2?
Right side of 2. Right? It's a stack of calls. Right? Oh my god, math too.
Gotcha.
Jesus, guys. Come on.
Jeez.
You guys are being... Oh my god. Oh, totally. Dude, you said you were gonna stop doing that until you got the new one. That's like the 3rd time you said last time until the new job. So help me God, totally. I will get you that new job so I can feel better about this. You guys are insane. Oh, thank you all so much. Alright, so that's... Oh god. Oh, keep it together, keep it together, keep it together. Let's move this just a little bit. And let's delete this 15 for a second.
Yep.
So, we're still on the right side. You're alright, I forgot it. Oh, you suck. I love you guys so much. Jesus Christ. I didn't even know Hype Trains had percentages. It's at 200 fucking... Keep going with the algorithm. Keep going. You're at the right side of 2. Does that make sense?
Yeah.
Okay. So
Yeah. It does make sense because we go back down with the call stack.
Yeah. Keep going. So then what? Then what happens?
Then we go to 4. Then we go to 4.
Write it in the stack.
And then we check the left and right side of 4.
Write it in the stack.
Yeah. We go left, right, close it, and then we don't have anything left. Then we go back down to our stack so I can
Cross
exit
it out
2.
when it's done. Make sure to cross out 4.
Yep, and now we're... Yep. Oh, cross out 4, true. Sorry about that. And now we're back at 7. So now let's go to the right side of 7. Oh, shit.
Nah, dude. No, come on. I'm like barely holding it together right now. Thank you, CM.
Oh,
CM, you
man.
literally said you were lurking.
CM doesn't give a fuck. Yo, chat, let's get this guy. Let's get this chat. Let's get this hype train to a level it's never been to before.
Still lurking though.
Dan is such a great teacher. You know, this VOD is gonna be saved. It's gonna be a good teaching material for everyone else. Big shout out to the man himself, Rockstar74. Let's go!
What the fuck?
That's what I'm talking about, Beast.
I don't even know. Come on.
your hype train just destroyed Twitch. It just ran through all of Twitch.
I don't think it goes that high.
Yours just did. That is so awesome. I think everyone subbed. Yeah.
Oh my god, you literally broke the train. It disappeared. Milky, for the love of God, finish this algorithm before I die.
I can't, bro. I'm gonna die too. I'm gonna die too. Should I start crying? I cry with you? Should we both just start crying on stream?
I might be a little ahead of you there.
Okay. Let me finish this before we... Let's go. Yo, let's cry stream. Okay. Yo, we're still gonna cross tears. Alright. Go. It's part of the interview. Yeah. Dan, does this happen at every Fang interview?
Yeah, no.
At Facebook? And they're just gonna get a bunch of donations and start crying, and I'm supposed to be there. They're like, finish the tree! Finish the goddamn tree! I'm just gonna be sitting there dealing with like what to do.
Oh my god, let's go. Rollers, thank you. Raw, thank you. Ghost,
Okay.
thank you. Fairy,
Okay.
thank you. Beast, Jesus, thank you. CM, everybody, totally. Holy crap. Ugh.
I'm gonna just continue
Please,
over here. Don't mind me,
please,
guys.
Please.
Stream, don't mind me.
Oh my god. Oh my god. Oh, Jesus. Oh, okay.
We got 15. There is no left side. Let's go right side, which is 16.
Oh god. I'm gonna just stand up for a sec while you finish this. Oh, okay.
Right. So we got through 15. Let's exit that. It's normal the interviewee that is crying, not the interviewer. Well, we flipped it here. Yo, what's up, Mewtwo? Mewtwo. Alright, and then we will exit the right. We write down our output of 16. So now, after this, I'm prepared for any interview. I don't care what happens in the interview, you know, room. They can't top this. So the boy's Gucci. Then we'll exit that. So there you go. So we have 7, 2, 1, 4, 15, 16, and we can complete our call stack. Oh, that's the wrong one. Mustache time.
I don't know what
All
that
right.
means.
There you go.
There you go. That's it. Congratulations. You simultaneously have handled
Thank you.
recursion, entries perfectly. Didn't account for didn't get tripped up by any nulls. Didn't get screwed. Even if the root is null, even if I gave you null from the start, you got it. Easy. You got it. You're crushing it. Okay. So, you are, God, hold on, give me a second.
Hey.
What's EQ? Emotional quotient. It means how much you feel other people's feels. So, like, if I started crying and Milky had started crying. Okay, so, this...
I don't have. So that means I have low EQ.
You have low EQ. There you go. So, congratulations, you very clearly did it. You have printed out each value in the tree. You did it recursively. This is an especially tough recursive, but because it has the two-sided, right? Which is why you got tripped up a little earlier, which is why you have to write it as this kind of LR. Right? It gets a little
Yep.
tough. Alright, hold on. I have to update my cry command. Dan, god damn it, has cried 15 times on stream. Oh shit, hold on. Commands, edit. Oh, I forgot how to do this. Okay. All right. So that's that. Now, here's the thing, right? The thing I didn't tell you to do was print it in a certain order, right? The thing I didn't ask you to do was anything very specific here. I just said print the tree, and now you've printed the tree. But now what I want to call your attention to is how easy it is to print the tree differently. And so now we're going to talk about tree traversals. Because what you've done is traverse the entire tree. You've now successfully seen what that looks like recursively.
Right.
But let's understand that there are multiple ways to do that. So I'm going to copy this left side, pop it back into here. Now, let's take our core function again. And I'm not going to worry about the ifs, but I'm going to talk about 3 different pieces of data.
Okay.
We're going to talk about left, right, and the parent, right? So that's like left, right, and current, whatever you want to call it. These 3 pieces of data can show up in any order, right? And there are words for the order you use. The 3 terms for this are prefix, infix, and postfix. And the way I like to write them is PLR, LPR, LPR, and LRP, right? Where do you print the parent? Do you print it prefix before the left and right? Do you print it infix in between the left and right? Or do you print it postfix after the left and right? Right? So these are the 3 different ways you can do that. So let's take a look at your code again. Right? I'm going to simplify your code. And it's just I'm gonna skip all the edge cases and all the if statements just because it's too much effort, right? So I'm just gonna say print root, print tree, root dot left, print tree, root dot right. Same idea, right? Doesn't account for the nulls and everything, but this would roughly do what yours just did, high level. Agreed?
Yep.
Which is it? Prefix, infix, or postfix?
For the parent node, right?
This whole algorithm. So consider root to be the parent, basically. Right? That's how I call it.
Oh, okay. So it's I think this one. It's definitely not postfix because we're doing we're the first line 1, I guess print root is happening before the recursion of root dot left, root dot right. So it's happening before the postfix. I don't think it's a prefix. I think it's an infix.
All right. So remember, this is the order of printing. In infix, you would print the left node first, and then you would print the parent, and then you would print the right node.
Oh, that's what those. Okay, so then it's prefix.
Good. So let me be clear here. This is like print slash.
Oh, gotcha. So prefix is parent left right, infix is left parent right, and postfix is left right parent.
Exactly. So this one is.
I gotcha.
Prefix.
This is prefix.
Yep.
This is prefix.
Now, let's give ourselves, for the sake of time, 2 new versions.
Okay.
Now I'm going to change the names, and I want you to move the order of the lines.
Okay. Let me know when I can move them.
Yep. You're good for infix?
Okay, so let me go here.
What's up, Yuxel? Thank you so much,
for-
bud. Already learning more than a Prime stream. Burned.
So if we're doing infix, we know it's left, right. Oh, I keep messing up the order every time I click backspace. So
Yeah, sorry, it's a little annoying. You can undo. There's an undo button.
just keep the names as infixes, like you have it in this. Like, would it be infix root dot left, print root, infix root dot right, or would we change those names as well? I'm guessing you just want me to rearrange the order at which those print statements occur.
Yep.
Yeah, gotcha.
And now let's do it for
Okay.
postfix. Prime only
Yeah,
dances
let me
during the
just-
stream. In this stream, we just bounce.
Oh man, I can't can't click that last one. Oh, there you go.
There you go.
Kind of finicky. All right. So and the last one, it's pretty simple. It's first we go. All we have to do is actually move this one, the print root, because we go left, we go right, and then we'll just do print root, which is our parent. So that would be my answer.
Great. Easy. So let's. Can you pull that up a little bit so it's not off the thing? Sorry.
Sure.
There you go. Kittle, you got it. Melky, you also got it. Super easy, super clear. These are
Yep.
basically the three things, right?
Yep.
Because it's a binary tree, so there's really only so many orders you can do. What if I want to search an arbitrary wide tree? Can you tell me the name of the algorithm? I can look it up. I believe at that point you're just doing either a breadth first search or a depth first search, and you treat it as a graph. If that's what you're talking about, space. Yeah. Oh, let's really quickly run through each of these, super fast, and I want you to give me the output of each of these. So I'm going to give you. We already know the output of prefix. You can copy this from before,
Yep.
but I still want you to go grab that and copy it for me if you can, just so we have this all on one screen. Oh, jeez, come on. It's always hard.
What? That I look what I copied.
What is
look
that?
what I pasted.
Amazing.
I don't know. I think it's your Twitch link.
Oh no.
Okay.
Well, I
I
guess
swear to
everybody
God.
has to follow. No.
Hold on. Copy, paste. There you go. Okay. So prefix, we got that. It's 72141516, right?
Yes.
So let's do it for infix. Let me just waddle my way over here. All right. I'm gonna post it here. Dan, you can fix it after. So infix. So let's go. So first, we go to. Okay. So we given our root node, root node, which is 7. We get passed into our infix. Infix root dot left. We call it instantly before printing. Then we go into second node, right away. Node. We again go straight into the second node.
Keep going. Well, what do you mean by second node? Left or right? Those are our terms.
Left. Sorry. I'm saying so left. So okay. So starting at 7, we call infix with node 7, and then we call infix again with root dot left, which is 2, right?
Mm-hmm. So root dot left of 7
And
is
then
2.
yeah. And then we recursively call that function. So we're back calling that, and then the root dot left of 2 is 1.
Mm-hmm.
Is our first print statement 1?
Put it down. And keep in mind, just everybody watching, we're kind of running out of space, but generally you always write these out because it's hard to keep track of in your head where it is. But as Milky's already gotten some familiarity with it now, he can almost kind of do it in his head a little bit. So now keep in mind our infix printing order, right? Keep very close attention to that LPR and what that means. So you just got your 1.
So just got the 1, which is the leftmost. There is no more oh wait, infix root dot left. So we got that left output, which is the 1.
Mm-hmm.
And then print root. Root of root dot left is 2. Then we'll be printing 2.
Put it down.
And then the next one is root dot right, which is 4. There you go. So if I had drawn my stack, what do you call it? Stack?
Call
my
stack.
stack call? My call stack.
Very close.
Thanks. Yeah, close. My call stack. I'm actually going back into the next level here. So I finished the 2. I'm back at 7. Now I print 7. I'm gonna give space there. So I print 7. And I go root dot right, which is 15. Wait, no, I don't print. My output's not 15. If I go into root dot right of 15, there is no root dot left.
Careful.
Okay,
There you go.
there you go. Yeah, I was overthinking it, but I
Little
got
bit.
it now.
Now, big
Yeah.
takeaway. What's the difference between the prefix output and the infix output?
The prefix output.
Look at the
So
numbers.
I'm actually
out.
doing my best. Yeah. I'm just looking at the numbers in my output here, and this little like box at the bottom here. It looks like it tackles the left side of the root node first, from top to bottom, and then it goes to the right side.
So yes, but let's look at the output as a whole, right?
one.
What's really
Okay.
interesting about that infix output? Ignoring the tree, just look at the infix output.
It's increasing.
It's all in order. It's exactly in order from least to greatest.
Oh.
Now, why is that the case, right? That's the magic of this infix traversal. You've said, inherently, by the definition of this function, infix of root dot left, print everything less than me. Then print me. Then print everything greater than me.
Wow. Yo, this is a mind fluff, dude.
Yeah, bro.
What? What? What the?
And that's why, as somebody has called out, a
How
lot
did
of what
that
people
happen?
call this is pre-order, in order.
What the kind of black sorcery, Dan?
Yeah.
I can't even hear you. I can't
Hello?
even hear you.
Hello? Can you hear me now?
I can hear you now. I got my headphones on, but damn.
And post order is also another way to name these.
What the Bro. Oh my god. Okay, hold up. So infix is in order. I like what Scooby said there.
Yep. Yeah. Pre-order,
Right.
in order, and
So it's-
post order is another way to say it. So postfix is reverse order. Now be
So
careful with that, Raw. Is pre-order? If it post order was in reverse, wouldn't that mean pre has to be in order? Right. Notice that in order is in between. Pre-order doesn't have an order to it. Right. It does like exactly what Melky said. It does the left tree. It does the right tree. It doesn't actually order the numbers at all. But there is a way you could potentially make in order go from top to bottom, go from highest to lowest. Melky, I'll postulate that question to you. This one's tough because it goes against
Hold up.
what I wrote.
I want to finish the post order.
So post order, right? So it is left, right, parent, right? So left, 1. Then the right, 4. Then the parent, 2. Then we're back at 7. We're doing the right. There's no left, right? So we're at the right of this one. No left, right. Here we go. So 16, then 15, then 7. So do you have 1, 4, 2, 16, 15, 7? Yes, perfect. Beautiful. Now,
Yeah, I do.
sick. Good stuff. All right, now, while I go get the water that I forgot, can you change your in order or your infix code to go in descending order instead of ascending order? So make the numbers decrease as they go instead of increase. It's a simple change, but think about it. All right, what do you got for me, Milky Baby?
I think I just switched root dot left, root dot right, and yeah, I just switched those two placements.
And how does that feel? Feel good about that? Confident in that one?
Yeah, I feel pretty confident in that one.
All right, let's take a look real fast. So,
Right.
root dot right, boom. You hit 16 first. Then you print the 15. Then you'll print the 7, and then you'll go on to the left of 7. And then the left of 7 will print the root dot right first, which is the 4. Print itself, 2. And then print the
Yep.
lesser, 1. Easy game. Well done. You now understand the core 3 traversals of binary search trees. Now, for those of you wondering, how valuable is this? When I interviewed with Microsoft, my first question on my first interview with them, before I went to the final round, was literally a binary tree prefix traversal. That's it. Literally a Microsoft question, right? Easy game. You got this, guys. Now that you understand this one, everything after this will be easier because a lot of it's very similar to what we just did. Thank you so much to everybody who donated subs today, who threw in bits today. That's literally going to pay my rent. So it means the world, guys. And yeah, I love you guys. Thank you so much for hanging out, and I will see you next time. Also, thanks, Melky. We love Melky.
See you guys.